So today we are going to look at the velocity and acceleration of a simple harmonic motion. In the previous video we had looked at the displacement of a simple harmonic motion and we obtained an equation for the displacement to be x is equal to a cosine omega t. I don't know what we called it, but that could have been maybe equation number 3. So we can actually build from there. X here represents displacement. A represents the amplitude of the motion, which is the maximum displacement. And omega represents the angular velocity, or if you like, the angular frequency, while t represents the time, or t stands for the time. So today we are going to look at the velocity of a simple harmonic oscillator. So we will start with our common knowledge that the velocity of a motion, recall that velocity of a motion is equal to the x dt. That is, velocity is simply defined as change in displacement as time changes. Change in displacement as time changes. So we are now going to substitute our value for x. What we have for x into this place, so that we can say that velocity is actually equal to d dt into x. We already know is equal to a cosine omega t. So it means if we differentiate this function, we are going to get velocity. Since a in this case is a constant, what we are differentiating with respect to is t, so a is a constant in this case. We are just going to bring out a, so we'll have that velocity v will be equal to a, then we say d dt into cosine omega t. So that's what we're going to have, because a is a constant in this case. Now this leads us to, or if we're going to differentiate this, we know that this is actually a function of a function. This is a function of a function. First of all, omega t is a function, and cosine omega t is a function of this function that is in here, such that we can separate this. We can separate this to be, we can take this to be cosine u, where u is equal to omega t. We can take this to be cosine u, where u is equal to omega t. So here we have a function of t, and here we also have a function of t. So if we call this, let's say we call this y, we can now bring in the chain rule. That's what we use to solve the function of a function. And what is that chain rule? It says if you want to obtain the y, the x, but in this case we're not differentiating with respect to x, so we are going to use the y dt. If you want to obtain the y dt, it is simply equal to du dt multiplied by dy du. So first, differentiate u with respect to t, you obtain your value, and then next you differentiate y with respect to u and put your value here. We will see that if we actually cancel out here, like u cancels out u, what is left here is dy dt, which is the same thing with what we have on the left hand side, so nothing changes. Now to do this, to go ahead and differentiate this, we will have dy dt is equal to, first let us differentiate u with respect to t. This is u equal to omega t, and if we differentiate u with respect to t, we are going to obtain omega. It's just like someone telling you to differentiate, okay, you are giving y equal to 2x, and you know that this 2 is actually a constant, so if you differentiate this, you are going to get the y, the x, is equal to 2. That's why when we differentiate u equal to omega t, with respect to t, we will obtain just omega. Okay, if we differentiate y with respect to u, so when you obtain the cosine of a function, when you differentiate the cosine of a function, you get minus sine. Minus sine, please take note. But when you differentiate the sine of a function, you get cosine. In this case, we are going to differentiate cosine of u, so we will get minus sine u. Minus sine u. Minus sine u. That's what dy dx will give us, or that is what d dt will give us in this case. So we can now have that. When we multiply these two, we get negative omega sine u. That's what we get here. But we already know that u is equal to omega t. So we can say that this is equal to negative omega sine omega t. That is the value we will obtain when we differentiate this. So we can now take this and plug in here. That gives us v equals a multiplied by negative omega sine omega t. If we multiply this, what do we get? We get v is equal to negative omega a sine omega t. We can actually call this our equation number 4. This equation gives us the formula to calculate velocity of a simple harmonic oscillator when what you are given is actually the angle, that is omega t, which is the same thing as theta, or the angular displacement if you like. If you watch, there is no x here. There is no x here. There's no x here. So this equation does not depend on displacement, but instead it helps us to obtain velocity from the angular displacement, which is omega t. As we continue, we are going to find the equation with which we can calculate velocity from displacement directly. So if you have any reactions, you drop those reactions on the comments. If there's any part of it that is not very clear, you drop your comments. And as well, for those who want some more clarifications on differentiations or just elementary calculus, you can also let me know, and I'll find time to make a specific video on that regard. So what we're going to do next will be to obtain the acceleration of a simple harmonic oscillator. Recall, we started with x equals a cosine omega t. We actually call this our equation number 3. Then we use this equation 3 to obtain another equation, which was v equals negative omega a sine omega t. We call this our equation number 4. So the next we will do is to obtain the equation for acceleration of a simple harmonic oscillator. This wouldn't take anything different. We already know by basic definition that the acceleration of a motion A is equal to the time rate of change of its velocity, that is dv dt. We can recall that acceleration is dv dt. So if acceleration is dv dt, then it means that acceleration is equal to, what do we do here? We have d dt, and then we substitute what we have as v, which is negative omega a sine omega t, and put it in here. So we have negative omega a sine omega t. So once we differentiate this function, we are going to get the acceleration of a simple harmonic oscillator. It's not a difficult one. Again, we simply place a equal to, because negative omega A are actually constants. They're not part of the function here. We're going to bring them out. We'll just separate them. So we'll have negative omega A. Then we'll now have d dt into sine omega t. Once again, this leads us to the differentiation of the function of a function, which I explained in the previous video. But for more clarity, I'm going to explain it again. We have a setup here that looks like, I'm just going to put it aside here. We have a setup here that looks like y is equal to sine omega t, which we can say that y is equal to sine u. And by that we mean that u is equal to omega t. So this is a function of t, and y is also a function of u, which in turn is a function of t. So that's why we refer to it as a function of a function. And like I said previously, if you want to differentiate the function of a function, you use the chain rule. What does the chain rule say? It says dy all over dt here. We're not using x, so we're using t. Dy dt is equal to du dt, that is differentiate u with respect to t, and then multiply what you get by what you obtain when you differentiate y with respect to u. U is equal to omega t. When we differentiate omega t, we will obtain omega multiplied by dy du. When we differentiate y with respect to u, it's like differentiating the sign of a function. So when you differentiate the sign of a function, you obtain cosine of that same function. Putting this together, we have omega into cosine u, which is exactly the same as omega into cosine omega t, because we already know that u is omega t. Now, having obtained this, we can now take this and substitute into d dt of sine omega t. And that leads us to acceleration A equals minus omega A multiplied by omega cos omega t. Don't forget that omega cos omega t is what we obtained when we differentiated sine omega t. So this omega cos omega t, we're only using it to replace this. We are using omega cos omega t to replace this. So that's why we have negative omega A multiplied by omega cosine omega t. And if we do that, we are going to obtain A, which is the acceleration of the simple harmonic oscillator, is equal to negative. When we multiply omega by omega, we get omega squared times A cosine omega t. This gives us an equation for acceleration. But we can actually simplify this further. If you look at equation number 3, it says that x is equal to A cos omega t. And that is identical to this. A cos omega t is equal to x. Therefore, A is equal to minus omega squared times x. We will call this our equation number 5. So equation number 5 gives us the formula for calculating the acceleration of a simple harmonic motion. If you look at this formula, you will see that acceleration A depends on x. Like we defined simple harmonic motion, we said it is a motion, the to and fro motion of an object which repeats itself after a given time, whose acceleration is directly proportional to the displacement. We can also see that there is a negative sign here. This negative sign shows that the direction of the acceleration is opposite to the direction of the displacement. While the displacement increases, acceleration will, while the displacement goes towards the right, acceleration will be going towards the fixed point. and vice versa. So this defines acceleration of a simple harmonic motion perfectly. A is equal to negative omega squared x, where x here stands for the displacement. So once again, in the next video, we are going to look at the energy of a simple harmonic oscillator. We will take time to break down the equation for potential energy, kinetic energy, and the total energy of a system, and then use those equations to obtain the velocity of a simple harmonic motion and its maximum velocity when displacement x is given.